Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Hello everybody and welcome to this presentation. In this lecture, we review a problem as a case study. The slides will be finished in this lecture and designing with Rosa software will be started from the next lecture to complete your study in this course. In a case study, for drinking water supply from groundwater, nanofiltration is needed because groundwater has polluted with Callisto herbicide. Callisto controls annual broadleaf weeds in field corn, seed corn, yellow popcorn, sweet corn, and other labeled crops. Callisto also delivers contact and residual control of broadleaf weeds, flexible application timing, and excellent crop safety. One of the best ways to remove 97 to 99% of all pesticides, insecticides, and herbicides from drinking water is with membrane or granulated activated carbon system. However, using nanofiltration, herbicide can be removed successfully. In this study, Callisto herbicide was measured in a maximum concentration of 1.45 microgram per liter, while the international standard for Callisto in drinking water is 0.1 microgram per liter. Determine the maximum cost for the purification of groundwater with nanofiltration per cubic meter water independence of system recovery and process pressure. There are three types of data as given values for this case study, as you can see here. First, operating conditions and economic data include produced flow rate 2,100 cubic meter per hour, annual operating time 7,800 hour per annual, operation pressure between 5 to 40 bar, rejection cholesterol at 1.45 microgram per liter is 97%, pump efficiency is 0.65, energy price is 0.1231 euro per kilowatt hour, and module price per square meter is 45.47 euro per square meter. Manufacturer's data of the applied nanofiltration membrane. This data can be determined from the test condition after the determination of the module, such as membrane area per element, permeate flow, filtration pressure, calcium sulfate rejection, and temperature. Chemical data such as molar mass in calcium sulfate, dissociation factor, and universal gas constant, as you can see this data here. In this slide, a list of formulas for this study has presented. Permeability, osmotic pressure, recovery, concentration of Callisto, pump power, investment cost, annual fixed cost, and annual maintenance cost. Now let's look at the procedures and solutions. Procedure. Step 1. Determine the minimal membrane area that is necessary to treat the feed volume flow. To do this step, At first, you must determine the membrane permeability of the used membrane. For this, use the manufacturer's data from the test conditions. Verify if the osmotic pressure of calcium carbonate in the test conditions needs to be taken account. Second, determine the maximum recovery under which the process can be operated without exceeding the limit value of Callisto in the permeate water. Proceed here iteratively and start with a recovery of 80%. Third, calculate the required membrane area according to the chosen pressure. Round up to a whole number of modules and neglect the osmotic pressure of Callisto. Step 2. Calculate the investment and operation cost for the plant. To do that, calculate the investment cost, annual fixed cost, annual maintenance cost, and determine the annual energy cost. Step 3. Relate the values which were calculated in step 2 to the produced water per cubic meter. To do that, first calculate the investment cost per cubic meter, annual fixed cost per cubic meter, annual maintenance cost per cubic meter, and determine the total cost per cubic meter. At first, you must select a suitable element from the manufacturer's website according to the feed source. As the feed source is groundwater, the nanofiltration elements for the brackish water is selected. As you can see here, two selected elements are suitable for this case. NANO-BW and NANO-BW MAX with an 8-inch diameter and 40-inch length. If you compare these elements, they are almost the same, just NANO-BW MAX has a little more flux and membrane area. But if you look at the feed spacer thickness, the right side is higher than the left one. From the fouling formation point of view, the element with higher feed spacer and lower flux has less fouling potential. Therefore, this element has been selected for this case study. Now, we follow the steps according to the procedure with determination of the membrane permeability. To calculate the permeability equation, you must use the data from the element catalog. As you can see in the selected element, permeate flow is 41.6 cubic meter per day with 37 square meter membrane area and 130 psi applied pressure from the test condition. Osmotic pressure has also calculated according to this equation that has calculated 0.73 bar. Now all the parameters turned out for this equation and you can calculate it. After calculation, the permeability for this membrane is 5.67 liter per square meter in hour in bar. To determine the maximum recovery, you can use this equation with the feed and permeate concentration and rejection rate from the catalog that with trial and error test, the maximum recovery for this case 87% has been calculated. Required membrane area for total feed flow can be calculated with the produced flow rate, membrane permeability, and pressure. As trans pressure is very higher than the osmotic pressure is neglected. Please answer this question on the page of this lecture in the comments. Why the pressure with 20 bar considered for this case? This is your homework. As you can see, after modification of membrane area, 18,500 square meter is the required membrane area for the total feed flow. Accordingly, the number of membrane elements has been calculated 500. For this case study, based on 500 membrane elements and 6 elements per vessel, 83 pressure vessels in 2 stages calculated, in which 55 pressure vessels for the first stage and 28 pressure vessels for the second stage, as you can see. In the second step, you can use these equations to calculate investment and operation cost, annual fixed cost, and annual maintenance cost. The module price for this case was €45. F is also a function of pressure and can be obtained from this table. €3,364,000 estimated as investment cost for this case, such that 1/10 of this considered as annual fixed cost and 0.15 as annual maintenance cost. Annual energy cost can be calculated using the produce flow rate, annual operating time, recovery, pump efficiency, and energy price. That for this case, the annual energy price is 1.98 in 10 to 6 has been calculated. In this step, the values which were calculated in the second step now calculated to the produced water in cubic meter. And as the equation asks to determine the maximum cost per cubic meter, the total cost of €0.1538 per cubic meter have been calculated. So, this lecture as the last lecture for the theory part finished. I hope these lectures were fruitful to you. We will start with Rosa software in the next lecture. Thank you for your attention.